So, as usual, there were some videos for you to watch about neural networks. We're starting neural networks today, and for the rest of the course, that's what we're going to be talking about. And so I'm just going to do a recap of the videos. Let me get my marker. To talk about what is a neural network, because it's not quite so clear. So for other things like linear regression, for example, we can just say, well, linear regression model says the output, the prediction is a weighted sum of the features, for example. Or for logistic regression, it was slightly more complicated. We took a weighted sum of the features, and then we put it through a sigmoid function. For decision tree, we said, well, the prediction is a bunch of if-else statements looking at the different features. So with the neural network, what's a bit confusing about it is that it's a multi-step process. So the way we actually talk about how we get from the inputs to outputs is we're going to do something a bunch of times. And that something is actually not that different from linear regression. We're just going to take our inputs, multiply them by a matrix, and then add some intercept thing, which we're going to call biases. But the difference is that when we were doing linear regression, we were just getting one output. So our weights, our coefficients were a vector. We dot producted them with our feature vector, and we got the output. But here, that weight thing is actually going to be a matrix instead of a vector, which means we're actually going to get a bunch of outputs. So it's kind of like linear regression, but with 10 outputs instead of just one output. And for each of those 10 outputs, you have your own set of coefficients. And so if you have 100 features and 10 outputs, you have this 10 by 100 matrix of weights. And so that's what I've tried to write down here, which is that you have your x, your features, you multiply them by some matrix, and you add some intercept, and the intercept is now a vector instead of just a number, because if we have 10 outputs, we have an intercept for each output. So that's kind of ingredient number one. And then we do this weird thing to it called h, which I'll talk about more later, but that's called the activation function. So we do this weird thing to it, and then we get not our outputs, but actually just our intermediate outputs. And that's where we have to start thinking differently, because we do this operation, and then if you call the features x0, I have that superscript L for layer. You could think if you do that operation to the first set of features, now you have this intermediate thing, which isn't actually your prediction yet. And in fact, you're going to do that whole thing over again a bunch of times. And however many times you do that, 5 times, you call that a 5-layer neural network. But you're really doing a bunch of things over and over again to get from your input to your output, unlike most of the things we've talked about. So there's a lot of notation. A lot of resources are going to use different notation. Let's look at some code together to see what happens. So I'm just going to make some random 5 numbers. So we're assuming we have 5 features, and this is just one training example. And I'm going to make a 2 by 5 matrix here, just random numbers again. And I'm going to make h just squaring. H is just squaring the results right now. That's not a real thing we're going to use, but just for simplicity. And I'm just going to run this code just to show that like the simplest possible thing of a neural network is just as simple as this. We're going to make it more and more complicated, but this is the first building block. So all I've done is I've taken my feature vector, multiplied it by some matrix. Because this was a 2 by 5 matrix, I went from 5 numbers to 2 numbers. And so my output here is 2 numbers, and that's why you see 2 numbers. There's no meaning to them, it's just random numbers. But my output here is 2 numbers. And then I did this h thing to them. I just squared all the numbers. So this, you could call the prediction phase of a 1-layer neural network. And today we're going to talk pretty much exclusively about the predict in scikit-learn terminology. In other words, how you get from inputs to outputs. And then the fit in scikit-learn terminology we'll talk about on Wednesday, which is how does all the optimization happen. Any questions or comments about this? Okay, so here's another function then that's almost the same, except now W, instead of just being a matrix, is a list of matrices. So you can see down here when I call the function, I have W1, W2, and I've just put them into a Python list when I called them. And now what is this code doing? It's looping through, and I'm ignoring the bias here, the intercept called B, just for simplicity, but we can put that back in later. So what I'm doing here is I'm just taking my first W in the list, matrix multiplying it by X. So X was 5 numbers. Now I multiplied it by a 2 by 5 matrix. Now X is 2 numbers. Then I did this weird H thing to it. And that's where we stopped in the earlier function. But now I have a for loop. So I'm going to the next W in the list. The next W in the list is a 1 by 2 matrix. And so I take those 2 numbers. I multiply them by that. I get a single number, do the H thing to it, and that's why I only get a single number out. So I can run this code. And a few things to note here. One is that this 2 and this 2, the fact that they're the same is not a coincidence. For example, if I change this to a 3, I'll just get an error. And I'll get an error because I first went from 5 numbers to 2 numbers, and then I tried to multiply 2 numbers by 1 by 3 matrix, and that's not a valid matrix multiplication. So I really have to have some matching shapes here so that the matrix multiplication all works out. And so the thing that is ultimately very confusing about this is that there was that intermediate representation. We saw what went in, so we can even print, let's print X. So this vector went in, and this value at the bottom came out. But somewhere in between there, when my for loop was halfway done, there was this intermediate representation where there were 2 numbers being stored. And those are called the hidden, that's called the hidden layer, or those are the hidden units, or the hidden activations. The terminology is pretty bad here. There's a lot of things that mean the same thing and ambiguity, but that's going to be the sticking point where it's, I think, most easy to get confused because we're not used to having these intermediate representations. If we had 5 layers, we'd have a bunch of these intermediate representations. And we kind of have to think about them. And the reason they're called hidden is we don't see them. We kind of see the inputs and we see the outputs. But the inputs actually got transformed a bunch of times in the process. And it is useful for us to reason about those intermediate representations, which we're maybe not used to doing. Questions? Yes, Brian.
So when you took W1 and you multiplied it by X, so 2 by 5, 5 by 1, so you got a 2 by 1. Then you multiply that by X again? On the second pass of the loop, we have the output from the first pass of the loop, and then we multiply that by X again.
Yeah, so let me do that for you. So I took W1, multiplied it by X, and this was this hidden thing that I was talking about.
2 by 1.
And then I took W2, and I multiplied it, so let's call this hidden. And then I took W2 and multiplied it by the hidden thing, and got a single number out.
Oh, I multiplied the other way around. Okay. So then you get a 1 by 1. You get a single digit.
Yeah, but I should really this. And if we do this, we should get the same output, same 0.69 thing.
So the idea is you'll always end up with a single digit after you get the whole thing.
Well, we will get to that. If you're doing regression, then at the end you want a single number out, because just like linear regression or the polynomial basis stuff you talked about in feature and model selection, at the end of the day you're just trying to predict a number. And so, yes, you're going to want to... next class we'll talk about classification, where things are going to be slightly different. This sort of, the punchline is going to be if you're doing classification with 5 classes, you're going to want 5 numbers to come out, and those will become like the probabilities. So you do actually want multiple outputs for classification, but for regression, we're just going to get a single number out. Yes, Tom?
I just want to confirm with the notation that we're using. X is just the data we're passing in, W is our weights, and then it's passing out some sort of output, correct?
Yes, so that's right. X is a feature vector, a training example, whatever you want to call it. W, all the W's are all the weights. So the weights are now stored in a bunch of different ways. And then we would normally, have the biases too, or you could do the column of ones thing. And then the output is like our prediction. And so this training example X would have an associated target value Y, and we're going to try to train or optimize those weights so that we do a good job of predicting the target.
And then H is also like the hidden layer, or the hidden layer in quotation marks?
H is called an activation function, and we'll talk about it soon.
Okay, thank you.
Okay, so just a bunch of stuff to say here. These matrices do not need to be square matrices. That's what we just saw. We had a 5 by 2, a 1 by 2, all that kind of stuff. There's all kinds of terminology here, hidden states, hidden units, hidden neurons, activations. We'll need to get used to those. We are used to calling W weights, so that's all good. You're going to see these pictures a lot. I like these types of pictures. I think they're useful. So here's what this is trying to show. This is trying to show a case where you have 3 features. So each circle is a number. So those 3 red circles taken together make up the training example. And then in this case, you have 2 outputs. So you're trying to go from 3 numbers to 2 numbers. And you have a hidden layer with 4 numbers. And so you have a 3 by 4 matrix in here, or 4 by 3, depending on your convention. And then you have a 4 by 2 matrix in here. And so the point of these diagrams is that, let's say you have 3 circles here on input and 4 circles on hidden. You're going to have 12 arrows, 3 times 4. And that's exactly how many weights you're going to have in your weight matrix. A 3 by 4 matrix is going to have 12 numbers in it. And so each arrow corresponds to one of those numbers. And what it's saying is that this value is a weighted sum of these 3 values, and that's why you have these 3 arrows coming into it, which is just like the intuition from linear regression. And the second value is a weighted sum of the 3 inputs, and this third value is a weighted sum of these 3 inputs. And so those are the rows or columns of the matrix, depending on your notation. And so you could think of each of these arrows as one of those values in the matrix. Reiko.
Yeah, I was just going to ask, so when you're training the model, you're like specifying what number to put on each one of those arrows?
Yes, training the model, doing your optimization corresponds to picking the weights, which corresponds to picking a number associated with each arrow. Exactly. Okay, so we'll see a lot of these diagrams. They're pretty popular. Just wanted to say what they are. Important note. So we can actually have multiple outputs. We're not really used to having multiple outputs. Most of the stuff we've talked about so far just had one output, but we'll defer some of that discussion to Wednesday. And I just wanted to talk about a bunch of vocabulary. So deep learning, you've probably heard the term. It's pretty much the same thing as neural networks. I consider them synonyms. Artificial neural network, neural net, those are all the same thing as far as I'm concerned. Some acronyms, so NN neural network, artificial neural network, same thing. Convolutional neural network, CNN, that's what we're going to be doing next week. Layers are these steps that we do to get from the input to output. So if we do 5 of those transformations, we say it's a 5-layer network. The units, people call them units or neurons or activations. Those are just referring to the the values, those intermediate values. So you might see someone look at this diagram and say, oh, that's 4 hidden units, or that's 4 hidden neurons. They just mean that hidden layer has 4 numbers in it, or that. So just like what we were talking about earlier. And yeah, it can get very confusing. So hidden, visible, we talked about that. Activation function or nonlinearity refer to the H. We'll talk about that soon. ReLU and sigmoid are some examples of activation functions. We'll talk about that soon. And then you may have heard of backprop or backpropagation. That refers to how the derivative or the gradient is computed so that you can do your optimization. And so we'll talk about that on Wednesday as well. But my point is there's just a lot of weird sounding words in this field, and you'll have to kind of get used to that. So such is life. Now we're going to do some true or false questions. So why don't you take a minute and read over this first group. So I mentioned that I would talk about activation functions. So let's talk about activation functions. This H thing from before is called an activation function, and the first question is, why do I need H at all? And the answer goes back to what we saw at the very beginning, which is we're just doing a bunch of matrix multiplications. Again, I'm ignoring the bias. We can do the column of one thing or put the bias back in, but the concepts are really about the weights. So if I had no H at all, then I would have my prediction equals, say, W2 times W1 times X, my input. And the problem is this. Problem is that what we mean is that, right? We mean first multiply W1 times X. That's what we had in the code earlier. We had that for loop with the list of weights. So we first multiply W1 times X. But unfortunately, the way the universe works is that's the same as this. And so in other words, this is still a linear model. We have for some reason written this thing, W2 times W1 is just another matrix. And we have for some reason written that other matrix as the product of two matrices. But it makes no difference. If this is 5 by 2 and 2 by 1, we might as well just have a 5 by 1 matrix here. The complexity of the model is it's still just a linear model. This is still just linear regression. But the whole point is we don't want to do linear regression anymore. We want to learn some nonlinear mappings from X to Y. And so by putting that H there, if I say my prediction is W2 times H of W1X. I've just done something weird to it so that this is no longer the case. That's really what this is all about. Because now I've done a linear operation, then some weird nonlinear thing, and then by repeatedly doing this process, I can actually get more and more complex functions by adding more and more layers, because that's kind of the point. We want to learn complicated mappings from X to Y. And so we need the H to get out of the linear world. Okay, so H pretty much always-ish is an element-wise operation, which means if you have some vector, so W times X is a vector, H is going to operate on each element of that vector independently. So with maybe one exception that we'll talk about on Wednesday, you can think about that as being always true. So H of X vector is H of X1, H of X2, H of X3, da 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 da. So the funny thing about H is that all it really has to be is it has to just be something. If H is the identity, H of X equals X, meaning it does nothing, then we have this problem. But pretty much other than that, as long as it does something, then everything's going to work. Because by adding more and more layers, things are going to get more complex. So there's really a lot to choose from in terms of H's, and it's an active area of research as people are coming up with H that works better or makes the code run faster or blah, blah, blah. Because it's not super clear what the rules are for what a good H needs to be. Okay, so now I'm just drawing some of them. So the sigmoid function, this is really the same sigmoid function that we saw in logistic regression that took the raw model output and turned it into a probability. That's often used as the H in neural networks. Again, it isn't just a line, so hey, it's valid. Hyperbolic tangent is honestly pretty much the same thing as the sigmoid. It just maps to the range -1, 1 instead of the range 0, 1, but it's the same shape. You may see both out in the wild. Maybe around 2012, people started doing the ReLU, which is the rectified linear unit. So the ReLU, it is actually just h of x equals x if x is positive. So it is almost the one thing we're trying to avoid. But then on the left side, if x is negative, it just sets x to 0. So it's pretty surprising that, well, it's pretty surprising this works. But from a computational point of view, it is insanely fast to compute this function. Because you just, if it's negative, set it to 0. If it's positive, do nothing. Whereas, you know, computing some squiggly thing is slightly more work. So if you really, really care about computation, this is pretty nice. This is not smooth, though, and we're kind of supposed to worry about functions being smooth when we're doing optimization, although we haven't talked about it too much in this course. But people seem to just use stochastic gradient and not think about it too much, which is a little weird. But there you go. Then more recently, I don't know, maybe a couple of years ago, people started using the Swish activation function, which looks it's basically a smoothed version of the ReLU. What's interesting about it is it's the only one that's not monotonic, so it actually goes down and then back up. So long story short, this is a hyperparameter, and you can use whichever one you want. And to make matters worse, you could, if you really wanted to, pick a different one of these for each layer. I mean, if you were really hardcore about it, you could pick a different one for each unit, but you don't really want a million hyperparameters to deal with. So there you have it. Any questions about this? Ryan?
Yeah, didn't you just say about when you introduced the array of H functions that each one was equally different?
No.
The H1, H2, H like...
No, they're usually all the same. So you have some, let me go back up, way up here. So back up to this from before. Right now I was doing x squared. Well, actually x squared, just numpy is automatically doing that element-wise on each thing. But just remember, w times x is a vector. And now I'm going to do that h thing to each element in that vector. I'm going to take the first element, pass it through the swish. Take the second element, pass it through the swish. Yeah, typically you would pick them to be all the same. It's just there's no rule saying you have to, otherwise it's not a valid neural network.
So that's what you meant by element-wise?
Element-wise means it's not some more complicated function where the first element interacts with the second element in some way. It's just you do a separate thing to each one. Jerome?
So is the major selling point that some of them cause it to run faster, or is there a choice that can make it better?
There's why, the question is, why would you pick one activation function over the other? Of course, I can give the same answer. I always give, just try them all and do the one that gives you a better validation error. But yes, there's computational speed issues. So up until now, for supervised 1 and supervised 2, there's been pretty much two issues you could run into: underfitting and overfitting. Your model is too simple, or your model is too complex. And I mean, maybe that's slightly an oversimplification, but that's more or less the two problems you could run into. With neural networks, we now have a third problem, which makes them a huge pain to debug. which is the optimization itself, because the loss function is not going to be convex anymore. And so you might run your gradient descent or whatever type thing, and it says I converged, but it's actually just a local minimum, and there's something way better elsewhere, which we did not need to worry about with logistic regression, did not need to worry about with linear regression, et cetera, et cetera. So what that also means is that the initialization of your optimization matters a lot. In the lab last week, you didn't care. I just said initialize with zeros. It doesn't matter. It'll get there. But now, if you start over here, you might end up there. And if you start over here, you might end up there, except it's a million-dimensional version of that picture. So it's really nasty. And so there's a lot of now possible new selling points of making changes that weren't there before. Like maybe using the ReLU is going to make the optimization less sensitive to how you initialize it than the sigmoid. That actually turns out to be true, more or less. So the list of possible selling points has expanded, and we'll talk about that throughout the next couple of weeks. But it's about how good does the model tend to do in terms of accuracy, about speed, about optimization, all kinds of things. A lot of it has to do with optimization, though, which we really didn't have to worry about all that much until today. Yes, Furkan.
So these activation functions, is there any physics behind all these weird-looking functions?
Is there any physics behind? Well, these ones were kind of inspired by, so I'm not going to go into the whole historical talk of neural networks being inspired by the brain, et cetera, but the sigmoid one is sort of inspired by the brain and was used more historically. But yeah, I don't actually know how some researcher would go about trying to design a new activation function. But I don't think I'm guessing their mindset is more computational. Sam.
So when we're using the ReLU activation function, don't we lose a bunch of information by absolute?
Yeah, it's pretty weird that, I agree. It's pretty weird that the ReLU works because whatever negative value you had, you just kind of throw it away. I wish I had a good answer for why this is a reasonable thing to do. My best guess is that 10 years from now, we will have moved on from this. I think it does have issues, but it really helped with this initialization issue and other issues, and so it was better than what people were using before, which was the sigmoid type thing. Yeah. Like suddenly we're in another thing that is new starting today is that we're talking about a field that is changing ridiculously fast. Like linear regression has been more or less the same for a while. This is like be completely different lecture if it was 10 years ago, and same for the next few weeks. So that also changes the feel of things and may result in things not making sense, not because of you, but because they actually don't make sense, because humans have not figured them out yet. So I'll try to help you determine the source of the problem if you're confused about something. Okay, software. So when do we have until? 11:50? Yeah, okay. So we have 25 minutes. Okay, good. Okay, so this table is no longer relevant. I made it for this class a couple of years ago. All we really care about these days, I think, is that most people will use either TensorFlow or PyTorch. And we are going to use TensorFlow for the simple reason that when I made this course, PyTorch did not yet exist. So I had the course. It was in TensorFlow. I'm just going to stick with it. The computational linguistics people are using PyTorch. I've heard a lot of good things about PyTorch, so maybe I will switch over it to one day. But the truth is both are used widely. OK, you can read, click, all those things on your own time. There's also scikit-learn's implementation of neural networks. It's just very, very limited. You can't tweak it nearly to the extent that you can tweak. So I should have said, we're departing from scikit-learn for the first time in our Python machine learning world because neural networks are so messy. that they kind of need their own thing. And furthermore, the fit function, the optimization is so computationally intensive that we need software that is super optimized, software and hardware, in fact, that is super optimized, and so we need to depart from the scikit-learn world. Just a fun fact that the scikit-learn neural networks were actually contributed by a UBC graduate student who used to TA for me, in fact. So just remember, these are all open source softwares. People out there are contributing to them, so that's kind of cool. Okay, so within TensorFlow, there is something called TensorFlow.keras, and we're going to focus on that. That's the kind of easiest to use version of things, and it's going to be good for our purposes. So here we go. I think some of the next couple of minutes were also in the video, but regardless, I think it's useful. So I'm just making up some data set, and here comes our first keras code. So let me go to the very top. So just look at my imports here. I've installed TensorFlow, which you'll need to do. I have imported TensorFlow.keras. Keras used to be its own separate package. Google hired the guy who made it and wrapped it all into TensorFlow. So that's my thing, TensorFlow.keras.models, import sequential. Where were we? Here, good. Okay. So of all the things I want to say today, one thing I really want to say is there's going to be a major departure from how we use Python to specify what we're trying to do. A major departure from what you're used to. What you are used to, I think, is something like this. Model equals support vector classifier, stick in the hyperparameters. You just have one line of Python code that calls the constructor of that support vector machine data type, and you just give it all the information about all the hyperparameters. Now, in fact, it's a bit similar to Pulp, which we saw in the algorithms course. In Pulp, we had an optimization problem, and we used many lines of Python code to specify our optimization problem. And then at the very end, we did problem.solve, and that's where all the computation happened with Pulp. It's the same paradigm here. We have a bunch of lines of Python code just to say what we're trying to do. And then at the very end, we have .fit, say, and that's where all the computation happens. Or it's a bit more complicated than that. But my point is, we have multiple lines of Python code to specify what we're doing. So I make my sequential thing. I don't even pass in any hyperparameters here. But I have a line of code for each layer that I want to add to the neural network. So I have a dense layer. Dense refers to this fully connected thing. That's what we're doing this week. That's like the vanilla regular neural networks. Next week, we'll talk about convolutional layers. So this says the following. I want 10 circles in my first hidden layer. That's what this 10 is. And this 1 says I started with 1 circle. I have 1 feature. And then I specified the activation function to be the hyperbolic tangent. And then I added another layer. And so this is only a 1 hidden layer neural network. It starts from 1 number, goes to 10 numbers, then goes back down to 1 number. By the way, when doing regression, so I told you the activation function could be anything but the identity function. That's true, except for the very last layer is special. For the very last layer, we typically do set the activation function to linear, which means a do-nothing function. And the reason is, well, imagine we're trying to solve a regression problem, and at the very end, we apply the sigmoid. Then we could only ever come out with numbers between 0 and 1. So that's just kind of silly. Like if the right answer is 5, and then we just squish it to be between 0 and 1 right before predicting, we can never predict 5, right? Which is kind of silly. So we want the prediction to be able to be any number. So we let it at the very last layer. And in fact, that's what I drew here, because I knew this was coming. We applied h here, but I didn't do another h here on the last layer, which is typical when doing regression. questions or comments? Victor.
How do we choose the activation in each layer?
Yeah, I mean, how do you choose the activation in each layer? Last I checked, ReLUs were pretty popular, but it's a hyperparameter. And maybe just to not drive yourself crazy to start, if you have 5 layers, just use the same activation function for all 5 except the last one, and then just try some different values of that. But there's going to be so many hyperparameters, and there are some in the lab. I ask you to think a little bit about some principled approaches to tuning them based on your human intuition, but for the most part, we don't really know. And that's one of many very big struggles with neural networks. Annie.
What is the kernel initializer, and why do we set it to that electron uniform?
Right. Where is that?
In the model.add dense blah blah blah.
But it.
Sorry, a little further. Sorry, a little further down.
Okay, well, we'll get there. But to answer your question, it's about how the weights are initialized before the optimization is started, because they do not just initialize to all zeros here. Yes. Yeah, Shivam.
Are there any custom activation functions the user can define themselves, or is it?
Yeah, you can probably define a user-defined activation function. You probably need to. Yeah, yes, you probably can. Yes, Derek.
Just in the overall scheme of things, adding all this extra complexity for regression helps. I mean, I'm looking at like linear models and I'm like, okay, this kind of makes sense. Like, let's do this, minimize our error, and then we're adding these activate. Like, it's just like we're just adding this complexity. I'm like, does this pay off?
I'm very glad you asked that, Derek. So Derek's question was, we're adding all this complexity. Does this pay off? Is it worth all the hassle? So the number one thing I do in the first week or 2 of Capstone every year is just tell the students over and over again, do not use deep learning until you are sure you need to. And then 90% of them realize they don't need to. And everyone's first thing is like, oh, I saw deep learning in the news. Let me get this LSTM with 1 million layers. And like, it's just usually it doesn't pay off. However, there are certain class of problems where neural networks are so good, the next thing is not even close. Like, it's no contest, basically. And those problems tend to have certain attributes, like large data sets, large amount of compute resources available to you, structured data. So next class we're going to talk about when your inputs are images or time series or things like that. So there are cases where it really shines, but for just a vanilla problem, no, it's often not worth the hassle, and I think it's a common mistake to start with this before starting with checking, making sure other methods are not going to work before you go to this. Akansha?
The number of layers you're adding, that is also an hyperparameter.
Yeah, the number of layers we're adding is a hyperparameter, but it's not like in the code number of layers equals 5. It's just however many of those lines of code where I add a new layer, that's going to determine how many layers.
So you're going to go step by step. Like first, hyperparameter optimization would be finding how many layers and then defining an activation.
Yeah, but you can see how big of a hassle this is going to be. But yes, finding the number of layers is part of the hyperparameter optimization. So, Tom.
So when we add like a new layer, does it like always like reconnect it for us, so we don't have to do it like manually like what we were doing above? Sorry, like we're doing like 10, right?
Yep.
And if you want to add like another.
Oh, yes. Right. Great. So yes, if I added another layer here, I would not need to specify the input dim, because it already knows the previous one is 10, so it's going to need a 10 by 15 matrix. You only need that on the first one because it doesn't know what that input dim is going to be.
Thank you.
You just told me, Shivam.
Yeah. Considering you have 2 models with same number of weights, will more number of layers
Yeah, no one really knows. The question was, given the same number, basically the question was, is it better to have deeper networks with more layers or wider networks with fewer layers and more units? I mean, that's pretty debated, and there isn't really a general answer to that. I mean, you see some crazy deep networks performing really well and some not that deep networks performing really well. I don't have an answer to that. Last question, Ryan.
That input dimension is just going to end up being a hyperparameter. Like,
No, this input dimension is not a hyperparameter. It's determined by the data. So it's just saying I only have one feature in my data set, which is true because I made up this data set over here with only one feature. Let me come back because I'm running out of time, Derek. OK, so the next thing is this compile step. Where TensorFlow does a lot of amazing things that we don't particularly want to do ourselves. So first of all, you specify your loss. So squared error, we're used to that. You specify the optimizer. So I'm guessing SGD is a valid option here, which is stochastic gradient. Atom is pretty popular. It's a bit fancier than SGD, but you can think of it as basically the same idea. There's still going to be a batch size and all that kind of stuff. But what this is going to do, so the whole neural network explosion was accompanied by a hardware phenomenon where everyone used GPUs to do the training. So if you haven't heard of GPUs, well, there's CPUs and there's GPUs, and GPUs were originally made for graphics, and now lots of people use them for neural networks. So I thought I used to have in this lecture, maybe I deleted it, the NVIDIA stock price for the last 10 years. But you can look it up. It's pretty ridiculous. And it's totally all about this. So yeah, that would have been a good investment. NVIDIA makes these GPUs. And originally, they were kind of a pain to program them. I remember, like, not that long ago, 10 years ago, it was a huge hassle to use them because you had to program in their special language, whatever. But now it's all abstracted. So you do your thing, you run this compile, it detects automatically what hardware you're using. Oh, I have a GPU, and then it turns it all into GPU code for you, and it's super convenient. So this has, it's gone hand in hand, this neural networks and the hardware. Because just the computation, as you're going to experience yourself this week in lab and next week in lab, it's just massive amounts of computation. And it being too slow is going to be a big problem for most people using neural networks. So they really needed super good hardware and software to try to speed everything up as much as possible. Anyways, this is extra step, compile. Then fit, you guys already know about fit. You guys already know about epochs. This is basically like model.score. And so this code will hopefully run. Oh, come on. OK, well, there's too much to ask for this code to run, apparently. Anyways, let me try it one more time. And if it fails again, we'll just move on. OK, I'll debug this later. It's fine. OK, yes, so this was also in the video anyways. OK, we have 10 minutes left. All right, sorry, I need to rerun my imports. Oh, Jupyter. Oh, this was what you were asking about, Annie. Yeah, so it's not initializing the weights with all zeros. I talked about it being non-convex earlier. So it turns out that if all the weights are 0, then the gradient is also 0. But it is not actually the global minimum. So if you initialize all the weights to 0, it'll just say it converged immediately and not actually do anything. So it's typically initialized randomly, and you can set like what type of randomness is it doing, like Gaussian or with what variance, all those kinds of things. So the default values for this is probably fine these days. Anyways, where was I here? Okay, good. Okay, so model.summary is your best friend. I would say to really understand the architecture of a neural network, by the way, when people say architecture, they just mean like number of layers, number of units, like kind of what it would look like if you drew it with that circle and arrow diagram. That's what they mean by architecture. To really understand what your neural network is doing, if you can look at it and count how many parameters it has, that can kind of check yourself that you really understand what's going on. So I think the first question on the lab is in fact that, where I ask you to count the number of parameters. But that has been pretty easy so far. Like with linear regression, I have D, coefficients, and intercept done, right? But here it starts to get very, very messy, and we'll get a lot more messy next week to try to understand, well, how many parameters do we actually have? And so model.summary can tell you that. So for example here, here's the code. So that first dense layer, the output shape, it keeps saying none here, just so you know, because it's reserving that dimension for having multiple training examples. So you know, if you have one feature, you could actually have 1,000 by 1. If you have 1,000 training examples, then it gets transformed. You have 1,000 by 10 because you still have 1,000 training examples. That's what this none is. So why do we have 20 parameters here? We have 20 parameters here because we started with one feature, so one circle. We went to 10 features, so 10 circles. That gives us 10 of these arrows. Plus, we have 20 biases, or well, we call them biases, because each circle in the output gets its own bias. So any questions about how I got to this 20? Anyone confused about how I got to this 20? Tom, okay, great.
Do they always have biases?
Yes, do they always have biases? Yes. I just wasn't really writing them earlier on, but yes. So for example, here we went from 10, a layer of size 10, to a layer of size 5. So we have a 10 by 5 matrix in there, or in other words, 50 elements, 50 arrows, 10 circles to 5 circles, 50 arrows, 10 by 5 matrix. So we have 50 weights, and we have 5 biases, because each of those 5 circles has a bias. So another way of thinking about that is each of these 5 circles is kind of like a linear regression situation from those 10 circles coming into it. Each of those 5 circles is a weighted sum of the previous 10 things plus a bias, so it has 11 parameters. However you want to think about it, we get 55 parameters, 50 weights and 5 biases. Then we go back to a layer of size 1. So we have 5 circles going to 1 circle. That's a 5 by 1 matrix. That's 5 parameters plus 1 bias is 6 for a total of 81 parameters. So really, model.summary, good stuff. I can print out the shapes, so this is nice. I have a 1 by 10 matrix, 10 biases, a 10 by 5 matrix, 5 biases, a 5 by 1 matrix, 1 bias. There's some notational issues here in that when you have a layer of 10 things going to a layer of 5 things, some people will call it a 10 by 5 matrix, some people will call it a 5 by 10 matrix. It doesn't matter, it's just, are you going to write WX or W transpose X? It's just a convention thing. There's nothing more to it than that. But just when you're reading these, Keras actually uses, I guess, the more intuitive notation. I use the one to be consistent with the video, but you can read this as I'm going from 1 unit to 10 units, and then I'm going from 10 to 5, and then I'm going from 5 to 1. So Keras's convention is that if you're going from 10 to 5, the matrix is 10 by 5. not 5 by 10. So that's what this note is. Da-da-da-da. Okay, 4 more minutes. So let's just go straight to this, and that's how much time we're going to have. So I'm using D with a subscript to say the number of units in a given layer. So in this slide that you're looking at, D0 is the number of features. So here 1, D sub 1 is the number of things in the next layer, D sub 2 is the number of things in the next layer, and so on and so forth. So if you actually just ask how many parameters you have, it's this kind of weird looking thing, but I just want you to understand what you're looking at here. D0 times D1, because if I'm going from 1 thing to 10 things, I have 1 times 10 weights, because I have a 1 by 10 matrix. And then D1 times D2, okay, because if I'm going from 10 things to 5 things, then I have a 10 by 5 matrix, or 10 times 5 parameters. And then plus da-da-da, all the way to the second last D times the last D gives me the number of weights. And then for number of biases, I just add up all the numbers of units except for the very first input layer that doesn't have biases. And so in total, I get this crazy looking thing. I think it is useful for you to look at this at some point and make sure you understand it. And then I also think it is useful for you to look at this and realize, wow, I could get a lot of parameters here. So in that video, the 3 blue, 1 brown video, there was around 13,000 parameters. But here, for example, if we have D1 equals, if we have all the different layers of size 1,000, then we have millions of parameters. Sometimes we can have billions of parameters. So this is new territory in terms of number of parameters, which means we could get massive complexity, we could get massive overfitting, so we have to be really careful about that. We have massive computational problems because it can be really slow and it's not convex and you can get stuck. And so yeah, going back to Derek's point from earlier, there's a lot to go wrong, but also a lot to go right with neural networks. Let me just jump down to here. Which is to say, today we talked about what a neural network is, and next class we'll talk about the training part. And it's just not going to be as simple as do stochastic gradient descent. There's going to be a lot of things we have to be very careful about when it comes to the training. Next class we'll also talk about classification and something called the softmax and regularization, which you'll be doing this week in 573. So that's it for today. See you in lab today and tomorrow, and see you in lecture on Wednesday.